Hello everyone, I am Nick, and today our group will represent a case study of Sitio Tingaan's recycling of used lead acid batteries. So here, this is our mind map, and our mind map emphasizes on the dangers of recycling lead and how we can go about breaking the cycle. But before we go too deeply about this, we're going to talk about the background of the study. Now, where is Sitio Tingaan? Actually, Sitio Tingaan is situated in the Cebu City. So, Cebu City, it is the capital of Cebu province and is the second most significant metropolitan area in the Philippines. Located on the eastern coast of Cebu Island, it is known as a vital domestic shipping port as it accounts for around 80% of the country's shipping companies and serves as a key center for commerce, trade, and industry in the Visayas and Mindanao regions. As of the 2007 Philippine census, Cebu City has a population of around approximately 2.7 million residents. The city's economy is largely driven by small and medium-sized enterprises, supported by developments like Cebu Business Park, which is seen in the picture on the screen, and the IT sector initiated by the Ayala Corporation. However, the informal recycling of used lead acid batteries, acronamed as ULAB, has emerged as a significant concern. With a single registered recycling facility in Mandaue City, this has led to the proliferation of unregulated recycling operations, particularly in Sitio Tingaan, which is situated in Barangay San Nicolas, where hazardous practices pose major health risks. About 2,000 residents in Sitio Tingaan, mostly children, are exposed to harmful heavy metals due to open-air smelting conducted near schools and homes. Despite interventions from local authorities and the Department of Environment and Natural Resources, the INR, informal ULAB recycling persists due to economic necessity, threatening public health and environmental safety. As Cebu continues to develop economically, addressing the environmental and health challenges posed by these informal practices is crucial. And that's what we're going to propose later on. A solution to this problem. Now, what do you see in this picture here? Actually, this is an image, not from Sitio Tingaan, but this is an image of a child. Or rather, sorry, of a man that is seen trying to recycle the lead that is found in batteries. If you can see the box beside him that are used lead acid batteries, they're not usable anymore, and he's trying to recycle it with a tool because for job security, feed his family. Now, our focus of the study is in Sitio Tingaan, and this is an area, a sitio is what we would call it, in Barangay San Nicolas. Now, in the left image, the big image, is a Google Street View picture of the area. And if you can see, it is rather I wouldn't say rundown, but it is definitely informal. And it is unlike registered recycling facilities where there would be proper proper buildings, proper areas, designated areas that are ensured to be safe for recycling. Now, in the top right image, you can see it's an actual image of the recycling operations that are conducted in Sitio Tingaan. And if you see the gate in the top right, That's the gate that is found in the bottom left part of the image. It's color different. So that man is actually recycling the lead from used lead acid batteries. And in the bottom right image is a satellite view with red circles representing the areas, or like the parts of the facilities that were found to have a high concentration of contaminants. Now, we're gonna do we're gonna show you the extent of how horrible, of how bad the situation is in Sitio Tingkaan. Now, the data here is provided by the TSIP program pure.org, while the graphs that you will see are made by us using Jupyter notebooks, Python, and related libraries. So, going for on our first image. So, there are around like 200 sites here in the Philippines that are categorized by the TSIP program by Pure Earth as dangerous, as toxic sites that are dangerous to the surrounding population. And now, if you see this, if you see the dots, the circles, it has a gradient of violet to yellow. And what that means is basically if it's violet, it's not so bad. If it's yellow, it's super bad. And that corresponds, violet corresponds to a blacksmith index, which is a continuous variable, or basically factor that categorizes how bad the environmental pollution of a certain toxic site. So, if you can see, out of all the sites here in the Philippines, there is only one site that has a blacksmith index of bigger than 7, and that is the one that is found in Sitio Tinggaan. And not only that, even if we compare it with the world, the toxic sites found around the world, even if this is already bad as it is, being the worst toxic site here in the Philippines, moving on to the next slide, we can see these are basically all the toxic sites in the world with a key pollutant lead. There's around like 1,671 sites, which is a lot. Because lead, fortunately, is still one of the more primary, or let's say infamous sources of contamination. So let's go on to the next slide. Now, this slide really emphasizes how bad situation here in Sitio Tinggaan. Now, out of all the toxic sites here in this slide, around 1,671, there are only 15 sites that have a blacksmith index of bigger than 8. And Sitio Tinggaan is one of them out of 15 in the world. Out of 15 in the world that are already out of 1,671 in the world. It's one of the toxic sites. One of the toxic sites are on the extreme end, on the higher end of toxicity, or rather, on the higher end of, let's say, how bad situation is. Now, it's basically a histogram of all the data presented before, and in fact, among all the toxic sites, which key pollutant was lead, Sitio Tinggaan had one of the worst BSI index. In fact, it is in the 98th percentile. Out of all the 1,671 sites, it's in the 98th percentile. That's how bad it is. Now, not only that, not only that, lead was not the only pollutant in the area. There were also other pollutants that were found. Um, and lead is actually one of the, let's say, average, or like just like a bit, it was a bit higher than baseline MRL. So what does MRL mean? So basically it's the minimum risk level. So if you go above this minimum risk level, you're essentially in the danger zone. So what is being recorded in this MRL? So basically it is the oral ingestion level that a person consumes every day of a certain contaminant. Now, if you consume a certain amount per day, and if you go above this MRL, you are in danger of having long-lasting health consequences of whatever contaminant you were ingesting. Now, here in Chichatingaan, even though lead was found to be the key pollutant, it's actually the observed oral ingestion levels that were obtained from actually examining the children, the population, the population surrounding Chichatingaan, or within it rather. Actually, lead was just a bit over the observed oral ingestion levels, which is just a bit above average. Above average, still bad because lead is one of the worst, or the worst contaminant here in this graph, but it was actually just a bit above average. Well, mercury is a bit more, just a bit above average as well. And you also there was also cadmium, copper, and arsenic. Now, how did we come to this? Like, how did this arrive? How was this obtained? And we were expecting just lead, right? And how was cadmium, mercury, copper, arsenic found in the site? Well, actually, batteries are not just lead. They're also made up of other elements. I mean, the case is plastic, and in order for the battery to work, lead is not the only component to make it work. You also have other components which are required for your battery to conduct electricity, to power a certain car, let's say. Now, here in this graph, well, it might not look that bad, right? Actually, this is on a logarithmic scale. Now, if you actually look it on a linear scale, this is how bad it was. And the arsenic contamination is all over the roof. It's over the roof. It's actually 668 times the minimum amount that you should be ingesting per day. It's crazy. Actually, from examining all the 15 toxic sites that were just at a blacksmith level over 8, we found that Sitio demonstrating a particularly acute environmental and public health risk. And among all the sites, it was exacerbated by several unique factors that distinguish it from other polluted sites. While all the listed sites face significant health risks due to industrial and formal processes, Sitio Tingaan presents a convergence of conditions that magnify both the risks and the actual harm experienced by the community. Now, the severity of the contamination, it is the only one that had exceeded, had a contaminant that actually exceeded 668 times. No other contaminant from the other 15 sites exceeded their MRL by that much. And also, it also had other dangerous levels of mercury, cadmium, and copper. But Not only that, there were multiple exposure ways that the contaminants were able to seep into the surrounding community. And that was through airborne contamination, soil ingestion, food contamination, water contamination. And worst of all, majority of the affected population were children and pregnant women because of its close proximity to school. And that is how bad this situation is. And even comparing it to other use-led asset ULAB sites from the Ravi River, Central Africa, Ganesh, and the Doya Ganesh. They were all hazardous. They're all sites that were labeled as hazardous. However, the problem with Sitio particularly is because it's informal. While these other sites had increased levels of lead contamination, the problem with Sitio Tingaan is because it's informal. So it actually affected the surrounding population more than these other sites because these other sites are regulated, registered. So the contamination were just contained within the area. Well, they had exceeding levels of lead contamination. The affected population was just the workers within these toxic sites. So, let's explain the chemical processes in what makes lead so dangerous. So why is lead so dangerous? Well, once lead enters your bloodstream, its ions can mimic the ions of calcium due to their similar ionic radii. In fact, their cationic form, when the charge is divalent, which means it is +2, has a +2 charge. Lead has a radius of 132 picometers, while calcium has a radius of 106 picometers. This allows lead to enter calcium channels in cell membranes. And this is represented by this equation. The left-hand side of the equation represents the open calcium channel that a divalent lead ion can bind to. Once that happens, enzyme inhibition occurs, which is represented by the equation below. Lead can bind to enzymes that require calcium for their function. This can displace calcium and inhibit the enzyme activity. This can disrupt calcium signaling, which is critical for many vital functions, such as muscle contraction, neurotransmission, and cellular responses to external stimuli. The entry of lead into these cells disrupts these processes and also potentially leading to impaired neurotransmitter release, altered cell signaling, and toxic effects. Finally, it can also interfere with hemoglobin synthesis. The equation below actually represents equations below represent normal hemoglobin synthesis and the not normal hemoglobin synthesis. Now, in the first equation, the top equation, the left-hand side of the first equation represents how hemoglobin is synthesized normally through aminolevulinic, which means aminolevulinic dehydratase, and its cofactor a divalent zinc ion. When lead ions replace zinc ions in the enzyme's active site, which is represented by the second equation, they inhibit ALAD's activity. Lead does not have the same biochemical properties as zinc and cannot support the enzyme function in the same way. So what about the high arsenic concentration that was observed at the site? Where did it come from? Well, again, lead acid batteries can contain small amounts of arsenic as an impurity within the lead alloy. It's also released during smelting. The high temperatures of the informal smelting process cause the release of arsenic compounds like arsenic oxides along with lead fumes. These arsenic compounds are not created from lead itself, but rather released from the existing arsenic within the battery components. Mhm. Now, intervention. So, what can we do about this? So, it's actually for the, we have three. Our solution is in three stages. First, containment. Second, decontamination. Third is sustainable development. So, containment. So, what can we do about this? So, it's actually easy. It's very simple. So, we can just simply use geotextile covers, such as the one in this image on the screen. Just basically just covers the soil where the contamination was found, and it just prevents the soil from um going to the air and um basically spreading the lead through the contamination through the air. And then after that we can evacuate the surrounding population. After that, we can finally perform decontamination of the site through three types of methods, namely chemical stabilization, phytoremediation, and soil washing. Chemical stabilization can be achieved through compounds such as phosphates of sulfur, phosphates or sulfur, while it can also be done through lime or pH adjustment. Interestingly, plants can also be used to remove the pollutants from the soil. These can either be sunflowers or mustards. Both of these methods require time, knowledge, and materials that can be hard to come by. Therefore, the third method, soil washing, can serve as a simpler alternative. This is the simple process of removing contaminants from soil using water combined with acids like EDTA or citric acid. Now, after this, what do we do? Is the problem solved just because we decontaminated the site? Because we cordon off the location and remove the pollution? No. Because we just displaced. We just remove the jobs of potentially dozens of people. Because unfortunately, this is the way or the only way that these people in hard economic situations are able to make money to feed their families, right? So that's why we have to talk about sustainable development. So former recyclers can be employed in safe community recycling programs or site cleanup, fostering environmental responsibility while providing jobs. Children of affected families should receive quality education, scholarships, and school support to break the cycle of poverty and formal labor. While education, the recycler themselves can equip them with new competencies in eco-friendly recycling, agriculture, and small business development, since microfinance and seed funding can enable them to start safer enterprises. Furthermore, collaboration with local governments should be done to establish supportive policies such as labor protection and inclusive redevelopment efforts. That's all. There are references, and thank you.